Imagine you're standing on a foggy hillside at night, and you want to reach the lowest point in the valley. You can't see far, but you can feel the slope of the ground beneath your feet. If you always step in the direction that goes downhill the steepest, you'll eventually arrive at the bottom. This simple idea, following the slope downward, is the beating heart of how most machine learning models learn. It's called gradient descent. Today we'll build it up from nothing, starting with the simplest possible hill. Let's strip everything away and draw one simple curve, a parabola shaped like a smooth valley. The horizontal axis is a single number we get to choose, which we'll call W for weight. The vertical axis is how bad our choice is, a quantity we call the loss. Every point on this curve answers one question. If I pick this value of W, how wrong am I? High up on the curve means very wrong. Down at the bottom means as right as we can be. Our entire goal is to find the W that sits at the very bottom of the valley. Of course, in a real problem we can't just look at the whole curve and point to the bottom. We only get to stand at one spot and feel around locally. So let's place a ball somewhere on the curve, off to one side, and see what the ball can sense from where it sits. What the ball can feel is the steepness of the ground right under it. On a curve, that steepness has a name, the slope, or in calculus, the derivative. It tells us how fast the loss changes as we nudge W a tiny bit to the right. Notice the sign of that slope. On the right arm of the valley, stepping to the right makes the loss go up, so the slope is positive. On the left arm, stepping right makes the loss go down, so the slope is negative. The sign of the slope always points uphill. This is the key insight. The slope points uphill toward more loss, but we want to go downhill toward less loss. So all we have to do is move in the opposite direction of the slope. Downhill is simply the negative of the gradient. Let's turn that into an actual rule for updating W. We take our current W, and we move it a little bit in the downhill direction. In symbols, the new W equals the old W minus the slope. That minus sign is doing all the work, flipping uphill into downhill. But there's a problem with taking the full slope as our step. If the slope is steep, that step could be enormous, hurling us clear across the valley and up the other side. We need a way to control how big our steps are, so we introduce one more ingredient, a small number that scales the step down. We call it the learning rate, often written as a little Greek letter eta. Our full rule becomes new W equals old W minus the learning rate times the slope. Think of the learning rate as controlling the length of the arrow we draw from the ball. The slope sets the direction and a base length. The learning rate multiplies that length up or down. A tiny learning rate means tiny cautious steps. Now let's actually watch the ball roll. We compute the slope, scale it by the learning rate, and take one step. Then we do it again from the new spot. And again. Each step, the ball feels the local slope and nudges downhill. Watch something beautiful happen as we approach the bottom. The valley flattens out near the minimum, so the slope gets smaller. Smaller slope means smaller steps all on its own. The ball naturally slows down as it arrives, easing gently into the bottom. This is why gradient descent is so elegant. We never told the ball where the bottom was. It found it just by repeatedly feeling the local slope and stepping against it. No map, no global view, only the ground underfoot. But let's not gloss over that learning rate too quickly, because it can make or break everything. Let's replay the descent with 3 different learning rates side by side and really see what each one does. With a learning rate that's too small, every step is a timid shuffle. The ball does move in the right direction, but it crawls. It might take thousands of steps to reach the bottom, wasting enormous amounts of computation. With a learning rate that's just right, the ball takes confident strides and settles into the minimum in a handful of steps. This is the sweet spot we're always hunting for. And with a learning rate that's too big, disaster. Each step overshoots the bottom, landing higher on the opposite wall than it started. The next step overshoots even harder. The ball bounces up and out, diverging instead of converging. So the learning rate is a genuine dial we have to tune. Too small and we wait forever. Too big and we blow up. This tension will follow us through everything that comes next, so keep it in the back of your mind. So far our world has been one-dimensional, a single knob W and a curve. But real models have many knobs tuned together. Let's take the smallest step up in complexity and give ourselves two knobs to turn at once. Now our loss depends on two numbers, call them W1 and W2. Instead of a curve, we get a surface, a smooth bowl. The two horizontal directions are our two knobs, and the height of the bowl is still the loss. The bottom of the bowl is still our goal. Looking at a three-dimensional bowl on a flat screen gets awkward fast. So let's flatten it into a map, the same way a topographic map shows mountains. We look straight down from above and draw contour lines connecting points of equal height. Each ring is a loop of constant loss, like a single elevation line on a hiking map. The outer rings are high up on the bowl, high loss. The tight inner rings are down near the bottom, low loss. The center of all the rings is the minimum we're chasing. Here's a lovely fact about contour maps. Where the rings are packed close together, the ground is steep, because height changes fast over a short distance. Where the rings are spread far apart, the ground is gentle. Spacing encodes steepness. Now, in two dimensions, the slope becomes something richer than a single number. At every point there's a direction of steepest descent, an arrow pointing straight uphill. That arrow, with both its direction and its length, is what we truly mean by the gradient. And here is the single most important geometric fact in this whole story. The gradient arrow always crosses the contour lines at a perfect right angle. Steepest uphill is always exactly perpendicular to the lines of equal height. Why perpendicular? Because if you walk along a contour line, your height doesn't change at all. That's the whole point of a contour. So the direction that changes height the fastest must be the one that leaves the contour as directly as possible, which is straight across it. To descend, we do exactly what we did before. Go opposite the gradient. We flip the uphill arrow around to get the downhill direction. And since the gradient was perpendicular to the contours, so is our downhill step, aimed straight across the rings toward the center. Let's watch the ball descend across the map. At each step it looks at the contour under it, steps perpendicular to that contour toward lower ground, and repeats. On a nice round bowl, this marches the ball almost straight to the center. The update rule hasn't really changed, it's just grown. Both knobs update at the same time. Each new weight equals its old value minus the learning rate times its own slice of the gradient. We're just doing the one-dimensional rule twice, once per direction, in lockstep. So far, so friendly. A round bowl is the easy case, where every direction is equally steep. But most real lost surfaces are not round. They're stretched and lopsided, and that lopsidedness is where gradient descent starts to struggle. Let's make our bowl long and narrow, like a stretched-out canyon. In one direction the walls are steep and close. In the perpendicular direction the floor is nearly flat and stretches far. This shape is called ill-conditioned, and it's incredibly common in practice. Now place the ball up on one of the steep side walls and let it descend. Remember the rule, it must step perpendicular to the contour under it. Because the walls are so steep, that perpendicular arrow points mostly straight across the ravine, not along it toward the goal. So the ball leaps across the ravine, overshoots the flat floor, and rides up the opposite wall. From there it steps back across, overshooting again. Instead of traveling down the length of the canyon toward the minimum, it bounces from wall to wall. This is the notorious zigzag. Almost all of each step's energy is wasted bouncing sideways across the narrow direction, while progress along the long direction, the way that actually matters, crawls forward at a painful pace. And we can't simply crank up the learning rate to hurry along the flat direction, because the same big step in the steep direction would overshoot even harder and diverge. The steep direction holds our learning rate hostage. This is the core pain of gradient descent. Let's step back and look at that zigzag path as a whole. Notice how the sideways bounces keep reversing direction, canceling each other out, while the forward drift always points the same way. What if we could let the consistent forward motion build up, and let the flip-flopping cancel itself? This is exactly the idea behind momentum. Instead of the ball's step depending only on the slope right now, we give the ball actual velocity, a memory of where it's been heading. Real balls have inertia. A heavy ball rolling down a canyon doesn't ping-pong off every wall. Here's how we build that memory. We keep a running velocity. At each step, we take a fraction of the old velocity and add the new downhill push from the gradient. Then we move the ball by that velocity. The velocity accumulates a history of pushes. Watch what this does in the flat forward direction of the ravine. Every step pushes the same way, so the velocity keeps adding up, growing larger and larger. The ball accelerates down the length of the canyon, exactly where we were crawling before. And in the steep sideways direction, there the pushes keep reversing, left then right then left. With momentum, those opposing pushes largely cancel out in the velocity, so the wild sideways bouncing gets damped down. The zigzag calms into a smooth glide. Put those two effects together and it's the best of both worlds. Momentum builds up speed along the consistent direction while canceling the contradictory bouncing. The ball sweeps down the canyon far faster and far more smoothly than plain gradient descent ever could. There's an intuitive knob here too. How much of the old velocity we keep, the momentum coefficient. Keep very little and it behaves almost like ordinary gradient descent. Keep a lot and the ball becomes heavy and slippery, gliding a long way on its accumulated speed. That heaviness has a small cost worth knowing. A ball with lots of momentum can coast right past the minimum and take a while to circle back, just like a real ball rolling up the far side of a valley before returning. It's usually a fair price for the speed we gain. Let's zoom back out and remember how far we've come from a single foggy hillside. We started with one knob and a parabola, and the simplest possible rule: step against the slope, scaled by a learning rate. We grew that into 2 dimensions and discovered the gradient as an arrow of steepest ascent, always perpendicular to the contour lines, and we simply walked the other way, straight downhill across the rings. Then a stretched ravine exposed gradient descent's weakness. The wasteful zigzag and inertia came to the rescue as momentum, accumulating velocity to accelerate the useful direction and cancel the useless bouncing. Every one of these ideas scales up untouched. A real neural network doesn't have 1 or 2 knobs, it has millions, so its loss lives in a landscape of millions of dimensions that no one can picture. But the ball still just feels the local slope and steps downhill. That's the quiet miracle of gradient descent. A rule simple enough to write in one line, repeated over a vast invisible landscape, is how machines learn to recognize faces, translate languages, and much more. It's a ball feeling its way downhill in the dark. If this made it click, subscribe for more visual math.